Hello बच्चों, सत श्री अकाल and namaste from my side. How are you all? Hi. So again, this is Indrajit Singh welcoming you all into the victory batch, right? For the aspirants, those who are on the most sensible platform for an aspirants, those who are preparing for JEE, NEET and advanced kind of examination, right? How are you all? So guys, I think this time we are going to be awesome. Yes, we are going to be awesome. How we are going to be awesome? Let's see. Okay, we started this series with the motion units and measurement, and we followed by motion into the 1D and 2D, and slowly it moved on to the Newton's laws of motion, work, energy and power, rotational motion, gravitation. Then we moved on to the entirely different part of the solids and fluids. After that, thermal properties, thermodynamics, and now we have reached right to an edge. Yes, only 2 sessions of this victory batch are remaining of the 11th standard, and soon the new things are going to come up, okay, into the most different way, okay, into the most different way. So guys, today I am going to discuss about the SHM, how SHM is a different, right, from the motions we have seen. Okay, lots of things we are going to discuss. Lots of things we are going to discuss. So are you all ready, guys? I think yes, we should start with an SHM. Before moving on to an SHM, I want to tell you all the things that we have seen, right? Till now, we have seen the rectilinear motion, the motion along the straight path in which uniform motion, uniformly accelerated motion, non-uniform motion, lots of things we have discussed, right? Lots of things we have discussed. Okay, the entire kinematics 1D is based on the rectilinear motion. Okay, the next type of motion, some of the spatial cases we have seen, we are defining it as the curvilinear motion. Okay, we are defining it as the curvilinear motion. Okay, curvilinear motion, the motion on the curved path. Okay, it can be the 2D also. Okay, curvilinear motion can be considered as a 2D, and even I must say some of the applications of the curvilinear motion, right, are resolved individually. See, as you all know, the 2D is the two individual 1D simultaneous phenomena going on. Two individual, you can say two simultaneous 1D phenomena going on. They combine, the resultant gives, right, the 2D. Okay, after that we have seen the cases of the projectile and the projectile motion. Okay, so I want to tell you all, the thing that I want to convey is, we have seen different kind of the motion, but whatever we are going to see into the next 2 hours of the lecture, it is a very spatial category. It is the spatial category of the motion. Okay, spatial category of the motion. So first of all, if I want to define the periodic motion, see, before moving on to the SHM, we are having the two shades. The first spatial category of the motion, that is a periodic one. After that, it comes the oscillatory motion, and SHM is the part of the oscillatory motion. Slowly, we are going to cover up, right, each and every aspect, everything we are going to see. We are going to see the cause, we are going to see the oscillatory, we are going to see periodic. Each and every point is going to get covered. So first, periodic motion. Rather than to move on any kind of technicalities, I am just writing a stuff that the periodic motion is the spatial category of motion. Spatial category of motion. Now students will be saying, sir, what kind of the spatial? Okay, is it included into physics or not? Yes, bacha, it is included. Okay, it is included. So it is, if it is going to include it into the physics, then what kind of the spatial it is, okay, lies in it, lies within it, right? Because the entire physics is like that only. We are not able to understand the minor stuff. Then how, right, we are going to understand the spatial category? Okay, how we are going to understand the spatial category? Okay, so in this way, I want to tell you all why this spatial category. Okay, understanding the logic behind why this spatial category will help us in understanding these things. Okay, the best example of the motion of a satellite. Why motion of the satellite is considered as the periodic motion? Why motion of the satellite it is considered as the periodic motion? So in this case, I want to tell you all. Let us take an example. If I'm talking about a specific satellite, it is taking 5 hours to complete a revolution around the sun. Okay. So if it is completing the first round in 5 hours, then for next round, the same amount of the time the satellite is taking. 5 hours, 5 hours, 5 hours, 5 hours, 5 hours, 5 hours, like this way. So it means in this kind of the motion, something is getting repeated at the regular intervals of the time. Something is getting repeated at the regular intervals of time. Motion of a satellite. Let's have the another example. Roller coaster ride. Let us take an example. If I'm talking about the specific path of the roller coaster ride A to B. Suppose if you are sitting inside the roller coaster ride and you are assigned 2 rounds. When the coaster moves right in between A and B, on the very first time it is taking 3 seconds. Into the second round also it is taking 3 seconds. Into the third round also it is taking 3 seconds. Into the fourth round also it is taking 3 seconds. Then why this some part of the roller coaster ride it is considered as the periodic motion? Suppose from a point where you are getting, right, the coaster is getting started. Okay, if it is completing into the one round into the 35 seconds, again into the second round it is taking the same amount of the time. Everything is fixed. Then why it is considered as the periodic motion? In the motion of the satellite, something is getting repeated at the regular intervals of the time. Roller coaster ride, some path, or you can say something is getting repeated at the regular intervals of the time. Motion of a pendulum. Right? Why this motion of the pendulum is considered as the periodic motion? Motion of the pendulum is like moving on this side, moving on this side. This is point A. Here also we can say that into the motion of the pendulum, right? In this case also we can say that at the specific interval of time, path is repeated. Now, students are in the chaos. Sir, you told us at the specific interval of the time the path is repeated, but all of those paths are not fixed. Path, see, I've given you the 3 examples of the periodic motion, right? If I'm talking about the motion of the satellite, then it is on the circular path or it is an elliptical. If I'm talking about the roller coaster ride, then it is a random thing. Okay. Again, if I'm talking about the motion of the pendulum, okay, it is moving like to fro, to fro, to fro. Then what is common in these 3 examples that will exactly define the periodic motion rather than to write it as the spatial category of a motion? Path repetitions. at regular time intervals. Path repetitions at the regular time intervals. Okay. Path repetition is there at the regular time interval is there. The selection of path is not there. Here the term is path can be any. Compulsion is, right, it should be repeated at regular time intervals. We are not interested whether it is a curvilinear path, whether it is performing the motion of the particle is on the straight line. We are not interested. For the periodic motion, we are only interested into a term that path repetition should be there at the regular time intervals. If you want to, suppose this is a cubicle room, suppose if you want to start from this point, you can take 1 minute, 1 minute, 1 minute, 1 minute. You can take 1 minute, 1 minute, half minute, half minute. Whatsoever path you want to select, you can. Whatsoever path you want to select, you can. It's your, what we can say, dilemma. Okay, but path should be repeated. So here, whatever the position into the wide, I told you all that the periodic motion is right, because the position of the particle right is expressed in as a function of time. Okay, it is expressed as function of time, right? It is expressed as function of time. See, I told you all that the periodic motion is quite a special category of the motion. Periodic motion is the special category of the motion. Why it is a special category? Because here we have seen the cases of 1D, we have seen the cases of 2D, we have seen the cases of everything, all kind of the calculus method and all kind of the path, the curvilinear motion, everything we have seen, but we haven't seen the questions till now in which the path, the same path particle is continuously, right, repeating at the regular time interval. We have seen the questions in which there is a possibility that path of the path maybe of the path by the particle has been repeated, okay, but not at the regular time intervals. And if you have seen this kind of the question, okay, I'm sorry for that, right, if it has been repeated, and the question exists, okay, then they might have said that this thing will come up into the SHM. Okay, this thing will come up into the SHM, right? So this is all about the periodic motion. Now, examples, okay, lots of examples we have seen into the periodic motion. The first one, right, motion of satellite, motion of a pendulum, motion of electron, this is completely associated to the Bohr's theory, okay, that will come up into the modern physics, okay, that will come up into the modern physics, right? So these are all of those sort of examples of the. Now how periodic, see, periodic motion, oscillatory motion, simple harmonic motion, all are the special category of the motion. Now students might be thinking, sir, if they are having, if they are the spatial category of the motion, then I must say all are represented as the function of time. Okay, all are represented as the function of the time, or more accurately, if you write it down, we can write it as x is equal to t plus capital T. All are represented as the function of time. Right? all are represented as the function of time. So how we are going to define, right? How we are going to say that oscillatory motion is a special category, but how really you want to classify the oscillatory motion, the SHM, and the periodic motion, the oscillatory motion, and the SHM. So for that, I want to give you all a very simple example. Please, if through this example, right, any sentiments of any specific students is getting hurted, I heartily apologize, right, from my side. Okay? I heartily apologize from my side if sentiment of the student is getting hurted from this example. The example is like, why I am giving this example before, whole human race it is having the n number of these civilizations into it. Can I compare the n number of the civilizations of the human races into the different categories of the motion? This is the first civilization, I must say it is a rectilinear motion. This is a second civilization, I must say, right, it is a 2D, that is a motion along the two paths. This is a third civilization, right, it is some of the non-uniform motion and some of the spatial applications, right. Among all of those human race, in the entire human race, among all of those civilizations, the most crucial, I can't say crucial, the most rigid civilization is the periodic motion. Why? The periodic motion is quite rigid from the nature. Rigid, it means the things that can be unchanged. Rigid, it means that things can be unchanged. Okay, rigid means that the things can be unchanged. Why this periodic motion is rigid and it is different from the other civilizations into the human race? Because this is having one different thing. All are having the freedom. Why this civilization is rigid? Because this is having a different thing. What kind of the different thing? They are having the compulsion that within that civilization, path should be repeated. Path should be repeated, right? Path should be repeated. Path should be repeated at the regular intervals of the time. This is the rigidness of this civilization. Okay, so entire human race, multiple civilizations, their history and the respective freedom and the characteristics. But why the civilization periodic motion is rigid? Because this is having the classification path should be repeated. Among this civilization, there exist small groups. Into this rigidness, they are adding an extra feature. Rigid means only to and fro. Only to and fro. Rigid means only to and fro. The civilization of the periodic motion, right, restricts their humanity into path should be repeated but at the regular time intervals. It depends on you which path you want to select. But among this civilization, there exist small groups. Okay, they are more rigid than periodic motion. Again, I am saying more rigid. Path is also fixed. And only this path should be repeated at the regular time intervals, right? Only this path should be repeated at regular time intervals. Only this path should be repeated at the regular time intervals. So here if we want to define the oscillatory motion, okay, what kind of the more rigid it is? the path is also fixed. In the periodic motion, the path is not fixed. There is only a single compulsion that path should be repeated at the regular time intervals. In the oscillatory motion, path is also fixed, right? In oscillatory motion, the path is also fixed. Compulsory to and fro at the regular time intervals. Right? To and fro at the regular time intervals. Okay, so this is what the oscillatory motion is all about. Okay, this is what the oscillatory motion is all about. Now here comes, see, all oscillatory motions are represented by this equation. Okay, all oscillatory motion, all kind of the oscillatory motion are represented by this equation. F is equal to minus kx to the power n, where n is equal to 1, 3, ... into the value of odds. Right, all oscillatory motion. Why F is equal to minus kx? Right, I'm going to give you all this proof into the spatial this SHM. Right, I am going to give you all the proof of this, right, in an explanation into the simple harmonic motion. Okay, so path is fixed, to and fro. All of those oscillatory motions are represented by this single expression in which the value of the n is getting changed. Okay, in which the value of n is getting changed. Okay, now see how the periodic motion differs, right? This is a very simple. This is the periodic, right? And this is an oscillatory. How we are going to conclude this? It's periodic versus oscillatory. Okay, this is the civilization. This is the part of the civilization. This is having a freedom to select your own path, but the compulsion is the path should be repeated at the regular intervals. This is having not providing you the freedom even for the path selection. Here path is also fixed, to fro, and you have to perform it at the regular time intervals. You have to follow that path at the regular time intervals. Right. So in this way, I am going to write down this statement: all oscillatory motions are periodic, but all periodic are not oscillatory. All oscillatory motions are periodic, but all periodic are not oscillatory. Okay, all periodic are not oscillatory. Okay, all of those small groups are part of the civilization, but entire civilization is not a part of a small groups. Okay, apart from this, okay, the many types of the categories. So this is a spatial note from my side. Okay, now here comes another different category of the motion, and that is the SHM. Human civilization, human race, multiple types of motion. Specific civilization with more rigidness, periodic. Among that, small groups, right? Path is also fixed. Regular intervals, it should at the regular time intervals it should get repeated. Okay. SHM is more rigid than the periodic motion is rigid. More rigid, here comes the oscillatory. Okay, and now the rigidness is getting increased and we are reaching up to the simple harmonic motion. What does the simple harmonic motion states? Right? Simple harmonic motion states that SHM. Okay. I told you all of those, the oscillatory motion are represented by this equation. All of those oscillatory motions are represented by this equation, F is equal to minus kx to the power n. Right. So what is different into the SHM? The SHM is a oscillatory motion but with very small displacement. With very small displacement. If we are taking n value as 1, then we are having f is equal to minus k of x. This is nothing else but the responsible thing for a particle to perform the SHM. How this force is responsible for particle to perform the SHM? We are going to see how this force is responsible for a particle to perform the SHM. We are going to see this stuff. But in another sense, SHM is also a simple thing, to fro at the regular time intervals. But now we are going to see this explanation. I told you all that f is equal to minus kx to the power n. All of those oscillatory motions are represented, expressed right by this equation. But how this is going to be the reason for the SHM? This is going to be the reason of the, what is an actual reason of the rigidness, the cause of SHM. Okay, now we are going to understand that stuff. For that, let's take an example. This is a rigid wall having spring. Mass is attached to the spring. Okay, actually before discussing on the reason, some of the parameters of the motions are discussed, but slowly we are moving on to that stuff. Okay, slowly we are moving on to that stuff, right? Slowly we are moving on to that stuff. So causes of SHM. Causes of SHM. Suppose this is the reference point from which the particle is going to start its respective motion. What happens here? Particle is going to start its respective motion. See, suppose a gentle push is given. Okay, a gentle push is given. Okay, whenever the gentle push is given, a small restoring force is developed. F is equal to minus kx. Okay, this F is equal to minus kx, right, will ensure that particle will come upon its original position. Why? Particle will come back to its original position. Right? Particle will come back to its original position. So F is equal to minus kx will ensure. How? A gentle push it is given. Particle is getting displaced from its original position, right? Let's say this displacement is x. For this displacement of x, the same amount of the F is equal to minus kx. The restoring force is developed. Okay. So this restoring force ensures that particle is coming back to its original position. Now what happens here? Whenever it is getting displaced at the distance x, it is having the maximum amount of the potential energy. And when it comes back to its original position, that entire potential energy is transformed into the kinetic. So as because of this, I think we are going to discuss that part into the detail. Okay, here. Just hold on. See what happens here. This is a reference point from which particle is going to start its motion. A gentle push it is given and is going to reach up to the maximum displacement. See, whenever we are having the max displacement, it means that spring is elongated by x. So it means that at this point, the same amount of the restoring force is acting, F is equal to minus kx, that will ensure that particle is going to come back to its original position. Particle is going to come back to its original position, F is equal to minus kx. Right? Particle is going to come back to its original position, F is equal to minus kx. Right? So in this case, what happens? Right? In this case, what happens? If F is going to become off, right? Now, at here we are having the maximum potential energy. Okay, now while coming back to its original point, that entire potential energy is converted into the kinetic energy. but this time he is having the velocity in this direction. So obviously whatever the kinetic energy he is having is going to convert back. So again here on the opposite side, by the x amount, here by the x amount the spring is elongated, here by the x amount the spring is getting compressed. By the x amount the spring is getting compressed, here by the x amount the spring is getting elongated. Again here maximum potential energy, and here the restoring force is going to ensure that particle is going to come back to its mean position and original position. So like that way. Now what is the difference between the SHM and oscillatory? Here in the SHM the displacements are quite small. The value of x is quite small. If value of the x increases, then it is an oscillatory motion. Like I am giving you all an example, right, to understand the exact classification or the exact difference. I'm going to give you all an example, right, that can you can really understand the exact difference between the oscillatory motion and the SHM. Oscillatory, small, SHM. The vibration of the mobile with respect to its mean position is an SHM, but the motion of the pendulum is oscillatory. The motion of the pendulum is nothing else but the oscillatory. Okay. Now we are going to understand some of the basic parameters of it. Okay. To understand the basic parameters, okay, we are going to again take back this example. First parameter is mean position. At t is equal to 0, particle start its motion. At t is equal to 0, particle starts performing SHM. At t is equal to 0, particle starts performing SHM. Okay, at t is equal to 0, particle starts performing the SHM. The position, right, the reference point about which it starts. The reference point about which it starts. Okay, that is nothing else but the mean position. Okay, that is nothing else but the mean position. Okay. The second parameter is max displacement, that is amplitude. Maximum displacement of the particle with respect to the mean position. Suppose from this position particle is getting displaced maximum up to this. Okay, then I must define is axis plus a. This is a maximum displacement, and plus a, right? A is defined as the amplitude. Now here comes upon the maximum displacement on the opposite side. This is also the amplitude, but onto the negative part. Right? Time period of the oscillations. Okay. Angular frequency. Actually the thing comes upon like whenever the particle moves like this way. Actually as because of the restoring force it moves like this way. Right. So here comes the concept of the angular frequency. This is a very basic definition that we all are aware of. So we are not moving on to that part. Omega is equal to 2 pi f. And the time period of the oscillation starting from mean position A, C, O, A, B. What is the time period of the oscillation? Time taken to cover the path O, A, O, B, O. Right? Okay. Time taken to cover this much path Okay, that is nothing else but the time period of the oscillation. That is nothing else but the inverse of the angular frequency. Apart from this, acceleration, velocities, and lots of things are involved. Acceleration, velocities, and the lots of things are involved. Okay, now suppose let us take an example. Particle is starting from the mean position. Let's say x is equal to 0. This is t is equal to 0. Okay, mean position is not fixed. Mean position may get changed, right? But right now I'm defining it as a mean position. How the acceleration and the velocity parameters are defined and are getting associated with it. If the position of an SHM is the function of time, okay, and if I'm differentiating this position, then velocity is also function of time. If I'm differentiating the velocity with respect to time, then here comes upon the acceleration, it is also the function of time. But more clarification about this expression, it is going to come up into the Phasor method, right? It is going to come up into the Phasor method. Now see here. Suppose if I'm talking about the mean position, here velocity is maximum. This is an max displacement, that is amplitude. Okay, here it is a max displacement into the opposite side. What happens here? Particle starts. Here velocity is maximum at the mean position. Okay. Acceleration is 0. See, if I'm talking about the restoring force F is equal to minus kx, then can I say ma is equal to minus kx? Then acceleration is minus kx by m. So the acceleration, right, is associated somewhere with the restoring force by this equation. Okay, acceleration is somewhat associated with the restoring force with that specific equation. A is equal to minus kx by m. Right, A is equal to minus kx by m. So what happens here? Here velocity is maximum, but as x value is 0, so here the acceleration is 0. It means if acceleration is 0, so at the mean position, spring is in its natural length, no elongation, no compression is there. Now slowly velocity decreases. At the maximum displacement, velocity is 0. Elongation is maximum, so as of that reason the acceleration is maximum. Elongation is maximum, so as of that reason the acceleration is maximum. But acceleration, as restoring force is acting towards its center, right, the acceleration is also directing right towards the mean position. Acceleration into the SHM is always directed towards its mean position. Acceleration is always directed towards its mean position. Now here acceleration is maximum, velocity is 0. It means, and the direction of the acceleration is towards the mean position. It means it is, we are going to ensure, it is, the particle is going to ensure that it is going to come back to its original position. Now here the acceleration is maximum. Acceleration is going to decrease. Again the acceleration is going to be 0 and velocity is 0. Velocity is going to be increased, right? And here velocity is maximum. Again the same situation appeared. Velocity maximum, acceleration 0, slowly at the maximum displacement, velocity 0, acceleration maximum. Now acceleration is acting towards the center, so it will ensure that particle is going to come back to its original position. So here again the acceleration is slowly is going to decrease while coming back to its mean position. Spring is in its natural length, no elongation, no compression. As of that reason, 0 acceleration, velocity is maximum. But this time the direction of the velocity is reversed. Direction of the velocity is reversed. So what happens here? Again velocity is maximum, higher. velocity decreases, right? And here, now acceleration obviously again acting towards its center. Slowly it is going to ensure that we are going to ensure that acceleration, through this acceleration, the particle is going to come back to its original position. Okay, again maximum acceleration, slowly acceleration is going to be 0. Why? Because at the mean position, right, the velocity is getting 0, maximum, right? So like this way, to fro is going on. F is equal to minus kx is a responsible thing, and this is how the acceleration and the velocities are getting varied. Okay. Most important thing that I want to define is, if SHM is defined as the function of time, it's all about to and fro, right? So can I write down this equation as x is equal to a sine of omega t plus phi? Why I took sine function? Even I can take it as a cos function also. Okay, some students might be thinking, sir, why you have taken x, right, like this way? You can take it as a y. Okay, x states displacement into the x direction, y states displacement into the y direction. We need the position of the particle should be repeated at the regular time intervals. See, in physics, if any activity that you want to express in terms of mathematics, right, then you need a proper logic behind it. To and fro, it means each and every position should again come back, right, after the regular time intervals. It means we need that kind of the mathematical expressions in which the value should be repeated at the regular time intervals. Values should be repeated at the regular time intervals. As of that reason, sine and cos are right, taken as an expression to define the SHM. The proof of this, I will explain it into the Phasor method. I will explain it into the Phasor method, right? So suppose if I am differentiating this, again the velocity we are going to get it as a of omega cos of omega t plus phi. This is also, right, velocities, right, values are also repeating with respect to time. Again, if I am differentiating this, I am going to have the acceleration value negative a omega square, right, sine of omega t plus phi, right? Okay, again that same thing is getting repeated with respect to time. Okay, so it means that if I want to represent the SHM, I need that equation in which at regular intervals, see, let us take a very simple example. How to represent the equation of the SHM, right? Only the equation of the restoring force is not an equation of SHM. Suppose this is the mean position, right? Okay, this is the mean position, x is equal to 0. Right? At the regular interval of the time, it is reaching to x is equal to positive a. Right? X is equal to negative a. So at the regular intervals, the position of the particle is getting changed. 0 to a to minus 0, 0 to minus a to 0, 0. It means I need to, if you want to represent this SHM, you need that function whose value is getting repeated at the regular intervals of time. Velocity, here it is maximum, acceleration is 0. Here acceleration is maximum, velocity is 0. Again here acceleration is maximum and acting towards the center, velocity is 0. Right? Now, to represent motion parameters, we need a term that continuously repeats at regular time intervals.
That's why we are defining SHM, the equation of SHM, x is equal to a cos of omega t plus phi, right? Or x, suppose if it is performing into the y direction, then we are saying y is equal to a this is an equation of SHM. Right? Conditions to check, right? There are some specific conditions that will determine whether the particle is performing, right? Questions based on this are also asked in examinations, right? But it's okay. Why? See, value of the cos is getting changed between 0 to +1, +1 to -1, right? The minimum value of the cos is 0. Right, and the opposite either sides the maximum value is +1 and -1, right? Sine value changes in between 0 to +1, right, and in between -1, right? This is not only the reason that SHM is represented by this equation. Behind this there is a long derivation also, right? And apart from this, right, the entire Phasor method is based on it, right? Entire Phasor method is based on it. This is not only the reason, right? Okay, behind this there are there is much more thing to discuss. A lot of long derivation is there, but we are not interested in that part right now. Okay, and the entire Phasor method is also based on it, right? But the one thing is common, the value of the cos is getting continuously repeated. So as because of that, right, the value of the this will be the max displacement, that is known as amplitude. The value is getting cos as 0, the entire thing is 0, right? It means what is happening, the value of the x will be 0. So that will be the mean position, right? If the value of the cos is getting completely 1, x is plus a, then it is at the max displacement. Value of the cos entire is going to have the -1, then we are having x is equal to -a. Right? So this is how the position variation. Now let's differentiate this equation, right, with respect to time. Let's differentiate x, right, with respect to time. We get the velocity variations. V is equal to dx by dt. So that is equivalent to what? A of omega, right, negative sine of omega t plus phi. What is omega t plus phi and everything, we are going to discuss that in detail. And so these are the velocity variations. Suppose again I am differentiating, right, v with respect to time. We are having the acceleration variation. A is equal to negative of a omega square, right, okay, cos of omega t plus phi. In another sense, right, this part and this part, I want to discuss that thing in detail. Maximum velocity of the particle is a omega in terms of magnitude. Maximum acceleration of the particle is minus a omega square. If you want to write this equation, it is minus omega square x. This is a condition to check, right? This is a condition, right? Don't get worried, we are going to discuss this thing in detail. Right, here we are getting the new things. This is a maximum velocity, or in another sense it is also known as velocity amplitude, right? It is also known as velocity amplitude. In another sense it is known as acceleration amplitude. At this point, plus a is amplitude, right? A omega is the velocity amplitude, minus a omega square is an acceleration amplitude. Why this minus? This minus sign indicates it always, right, x towards the centers and opposes the move. It always x towards the center, right? So what is a condition? If particle satisfies the condition or the equation A is equal to minus omega square x, right, then we can say the particle is performing the SHM, right? We can say the particle is performing the SHM. So these are the equations. Now we are going to discuss these equations in detail and the respective parameters. X is equal to A. Let's take the easy thing to understand. Y is equal to A sine of omega t plus phi. Right? Omega t plus phi. What is Y? Position of particle at any time t. How the variation of the position of the particles are measured? What is A? Amplitude. Right. Now see what is this. Right. This is known as phase. The value of the phase is getting changed. As because of this, right, the value of the sign is getting changed. And as because of this, the position of the particle is getting changed. Similarly, in velocity equation, velocity of the phase is getting changed. Among them, the velocity of the particle is getting changed, right? Similarly, in the equation of the acceleration, the velocity of the phase, the value of the phase is getting changed, and with respect to it, everything is. So this phase, this is known as phase. What? Omega t plus phi. Phi is the initial phase, or it is also known as epoch, right? This will decide mean position, right? This will decide the mean position of the particle, right? The initial phase and epoch, this will decide the mean position, right, from which the particle is going to start. In another sense, can I say t is equal to 0 is going to, right, define the initial phase of the epoch. Second, omega 2 pi by capital T. This is known as angular frequency, right, of a particle that is performing an SHM, where T time period of one oscillation or round. Okay, so if I want to represent this thing, how I can represent? See, Y is equal to A sine of 2 pi by capital T into small t plus phi. Initial phase at t is equal to 0, that will show from which position the particle is starting its motion. Angular frequency with respect to this time period, at what time you want the position of the particle. So this capital T is time period, the small t is at what time you want the position of the particle. At what time t the y is known, right? So this is also an explanation about it, right? Similarly, the same thing happens for the velocity, right? And obviously there are some graphs related to it, right? There are some graphs related to it. And before moving on for the graphs, let's understand the one of the examples. First, if at t is equal to 0, particle is at x is equal to 0, what is initial phase? This thing is needed. Y is equal to A sine of omega t plus phi. right? At t is equal to 0, x is equal to 0. In another sense, let's take an example, y is also 0, right? Okay, y is also 0. So it means 0 is equal to a sine of omega t plus phi. We are getting the initial phase as 0, right? We are having the initial phase as 0. Second, if at t is equal to 0, y is equal to positive a, what is an initial phase of the particle? Obviously, what is an equation of SHM? Y is equal to a sine of omega t plus phi, right? This is in best example how the mean position is getting changed. Plus a, right, is equal to a sine of, right, omega t plus phi. From this point, the particle is starting its position. 1 is equal to sine of omega t 0 plus phi. So sine phi, that is equal to 1, phi is equal to, the initial phase is pi by 2. This thing is going to, right, help in understanding the concept of the phasor, right? Now third case, suppose if x is equal to plus a by 2 at, or y is equal to, y plus a by 2 at t is equal to 0, then what is an initial phase? Obviously y is equal to a sine of omega t plus phi, right? So in this case, what will happen? Plus a by 2, that is equal to a sine of 0 plus phi, sine of phi, that is equal to half, phi, that is equal to pi by 6. This is an initial phase of the particle. From this point, right, the particle starts performing the SHM, right? This is how the things are getting changed. Conditions to check whether the particle is performing the SHM or not. Suppose any random equation is given in the question. Suppose they said us that y is equal to a sine of omega t, right? They said us, suppose a particle is performing some random motion and the equation of the motion is represented by this. Check whether it is performing the SHM or not. Check whether it performs. Simple. It's very simple. Differentiate this equation, right? So velocity is equal to a of omega cos of omega t. Again, differentiate this equation with respect to time, right? Differentiate with equation with respect to time. We are getting acceleration is equal to minus omega square x. If this condition is satisfied, this condition is satisfied, the particle performs as such. Right? So like this way. Now graphs of SHM. X is equal to a cos of, or in another sense, suppose if you want to represent the first graph, that is displacement versus time graph. Lots of graph we are going to see, right? Y is equal to a sine of omega t plus phi, right? So this is the time, this is the displacement, right? Right, this is a displacement versus time graph. Second, velocity versus time graph, right? Velocity versus time graph, right? V is equal to a of omega, right, cos of omega t plus phi, right? Okay, in another, let's move on. Phi, we can remove this phi, right? We can remove this phi. Okay. Now velocity versus time graph. what will happen here? This is the variations of velocity, right? Okay, third equation, the acceleration versus time graph, right? What is an equation? A is equal to negative of omega square x, right? Okay, and that is equal to sine of omega t plus phi, right? Like this way we are going to have the acceleration versus time graph, right? So these are the three basic graph. Now let's move on to the fourth one, right? Velocity versus displacement graph, right? Velocity versus displacement graph. We saw V is equal to A of omega, right? And that is cos of, right, omega t. Okay, suppose if you want to replace this term, V is equal to A of omega, we can replace this as under root of 1 minus sine square omega t. By replacing this, we are having V is equal to, right, omega under root of a square minus x square. This is the equation of velocity with respect to displacement, right? This is the equation of the velocity with respect to the displacement, right? Now for this, right, the graph would be ellipse. Why? Suppose it is v square omega square, it is a square minus x square, right? So it is v square, it is a square omega square, right, minus omega square x square, right? So it is v square plus omega square x square is equal to a square omega square, right? And simply if you want to represent this term, okay, so this shows the graph of ellipse, right? This is x square by a square plus y square by, right? See, this is a graph I'm showing you. Right, okay, this is velocity and this is a displacement. Okay, so here it will be v square by a square omega square plus x square by a square is equal to constant. This is the equation of ellipse, right? This is the equation of ellipse. At this point we are having the maximum value of a omega, that is max velocity, and here we are having the maximum value of positive a. At this point we are having the negative a, and this point, right, we are having the negative a of a omega. Okay, negative a omega means direction is getting changed, magnitude is constant, right? So velocity versus displacement graph, right, it is what? The ellipse, right? Velocity versus displacement. So you can see this in the equation, that is v square by a square omega square plus x square by a square, that is equal to constant. Can I compare this to equation? X square by a square plus y square by b square is equal to constant, right? A and b are semi major axis and semi minor axis, right? So this is the value of the a and this is the value of the b. A is the semi minor axis and b is a semi major axis. I'm sorry, right? But that completely depends on the graph, how things are getting here. Value of the a and b gets varied, right? But it depends on the how ellipses been plotted, right? So this is the velocity versus displacement graph. Now third graph, that is the fifth graph, that is acceleration versus displacement, right? Acceleration versus displacement. Okay, acceleration versus displacement. Now let's see this graph. A, that is equal to minus omega square x. Now omega is it's constant, right? Omega is kept constant, so it means that a is directly proportional to x If A is directly proportional to X, obviously Y is directly proportional to X, right? Removing this proportionality sign, I'm getting Y is equal to mx, right? So this will be the equation, right? The graph will be of straight line. Graph will be of straight line, right? Graph will be of straight line. Right? Acceleration versus displacement graph, right? So it will be like this way, but here the slope is negative. Slope is negative. Why? A is equal to 9 minus omega square x. In that case, slope is negative, so graph is like this way, right? Acceleration versus x. I'm sorry. Yes, graph is like this way, right? This shows the theta is obtuse, right? And slope is negative. Similarly, if you want to calculate the force versus x graph, right, then we are having the same another, right? F versus x, right? Similarly, we can write it down as, okay, we can write it down it as, right, F, right? Or if you want to write it down it as MA A is equal to minus m omega square x, right? So force is equal to minus m omega square x. So this is also, right, the force versus displacement graph is also same, right? It is following y is equal to negative of mx condition, right? So graph is like this way, right? In this, the slope is minus, the slope is omega square. Here the slope is m omega square. There is only one difference. Okay, so these are the different graphs of the SHM. Now what is an actual difference between the oscillatory motion and the SHM, right? What is an actual difference between the oscillatory motion and the SHM? Now let's understand this thing, right? Come on everyone. As I said, vibration of the mobile, right? It is an SHM, right? Pendulum, it is the oscillatory motion. Okay, now before moving on to the energy, let's understand, right? We have seen we have seen the concepts of the periodic motion, we have seen the concept of the everything we have seen, right? Now we will understand the variations of the energy in SHM, and by one shot more than 10 to 12 examples we are going to see, right? First of all, we will move on to the concepts of the energies into the SHM, and by one shot we are going to see the all of the examples, right, for the concepts we have understood till now. Okay, so now let's move on to the energy in SHM. So students, let's move on to the energy variations in SHM. How the energy is getting varied. See, you can see this graph, right? We are going to see the equations also, we are going to see everything we are going to see, right? But here, first of all, in SHM, the most important thing that I want to show you all, that I want to write in front of you all, that no resistive forces are present. Right? No resistive forces are present. Okay, no resistive forces are present. So in this case, what will happen? See, according to the work energy theorem, work done by all forces, that will be change in kinetic energy of the particle, right? Work done by all forces will change the kinetic energy of the particle. Now, what kind of the forces are there? Right? What kind of the forces there is a possibility of what kind of forces it can do the work? Work is done by conservative, work is done by non-conservative, work is done by external, that will change in kinetic energy. right? So this is the negative delta U plus work done by non-conservative plus work done by external, and that is equal to delta Q. So it means here work is done by non-conservative plus work is done by external, that is equal to delta K plus delta U, right? Delta K plus delta U, right? Delta K plus delta U. Okay, so yeah, work done by non-conservative plus work done by conservative, right? That is equal to delta K plus delta U, right? Delta K plus delta U. Now what will happen? See here, no dissipative forces are there. It means work done by non-conservative force will be 0. Object is gently pushed, so work done by external agent is 0. So here whatever the variations are going on, right? Okay, it is in between the kinetic energy, right, and the potential energy. So in this case the mechanical energy is conserved and we are going to deal only with the kinetic energy and the potential energy. Everything is going at the one surface level, so there is no role of the gravitational potential energy, but yes, we are going to deal with the kinetic energy, and as spring is attached, the elastic potential energy is involved, right? Elastic potential energy is involved. So from this, right, one thing is confirmed. Kinetic is getting changed to potential, potential is getting changed to kinetic, kinetic is changing to potential, potential is getting changed to kinetic. But what is an actual equations of it and the graph? See, let's take the same example. This is a particle at t is equal to 0, right? This is the mean position of the particle, or in another sense we can take the right a reference point, right? Okay, now at the mean position the velocity of the particle is maximum. Velocity of the particle maximum, it means that it is having the maximum kinetic energy. Acceleration of the particle is 0, it means that potential energy is 0. Now you will be having one doubt, how the acceleration of the particle is associated with the potential energy. Acceleration equation was minus kx by m, right? Here x is an elongation or the compression that is measured in the spring, right? When external force is applied or in any conditions, right? X is an elongation or compression. At the mean position x is 0, it means elastic potential energy is also 0. Indirectly I can understand potential energy is not having any relation with, there is a relation, but we are going to discuss that into a different way. But acceleration is related to the compression and elongation, and even the potential energy is related to the compression and elongation. At the max point, at the max displacement x is equal to positive a, can we say that what? The velocity of the particle is 0, it means that kinetic energy is 0. And at this point acceleration is maximum, it means that, right, potential energy is maximum. Actually it is not that much 0. Whatever the variations are going on, right, it is going on between minimum and maximum, right? Nothing is perfectly 0, right? Here the velocity for theoretical purpose it is 0, but practically, right, okay, nothing is 0. Whatever the variations are going on, it is in between the maximum and minimum, right? Whatever the variations are there, it is between maximum and minimum. Suppose if we are moving on to the x is equal to negative a point, right? So at this point also, right, okay, the velocity of the particle is 0, so kinetic energy is 0, okay, and acceleration is maximum. In another sense, the potential energy of the particle is maximum. What are the equations? The simple, see here, the potential energy is associated with spring. First of all, the potential energy is associated, right, with spring. So it means that it is very simple thing. Potential energy, it is equal to half kx square, right? In another sense, right, if you want to replace the value of x, it is half x, that is a sine of omega t whole square. In another sense, the equation of the potential energy is half k a square sine square omega t, right? Sine square omega t. If you are, see, another equation is half ky square. I have replaced the equation of y. Some students might get confused. Sir, you have replaced the equation of x and you are writing here a sine omega t. You should write here a cos omega t. It's okay. SHM happens into the both direction. If it is happening into the x, then it is x cos omega. If it's happening into y, it depends, right? So this is the equation of the the potential energy, right? Okay, it's half k. Okay, now let's move on to the next equation, that is equation of the kinetic energy. Half mv square, right? The first equation of the kinetic energy is half m. If I'm going to see, there are two equations of the velocities. One, that is v is equal to a omega, right, cos of omega t, and second, that is v is equal to omega under root of a square minus x square. So suppose if I'm replacing that equation, that is, right, omega square a square minus x square. So I'm getting the first equation of kinetic energy, that is equal to half m omega square a square, or in another sense half m omega square, right, a square minus x square. Equation of potential energy half kx square. Equation of kinetic energy half m omega square a square minus x square. This is the first equation. The second equation of the kinetic energy k is half m. If I'm replacing the equation of v, that is a omega, and that is cos of omega t plus phi, or cos of omega t. So equation of kinetic energy is half m, right, a square omega square cos square omega t, right? If I am replacing the value of k here, we are getting the equation of potential energy is half m square omega square, and that is a square sine square omega t, right? So this is an equation. This is the first equation of potential energy. This is the first equation of kinetic energy. This is the second equation of potential energy. This is the second equation of kinetic energy, right? Here omega square, that is equal to k by m, right? Omega square, that is equal to k by m. Okay, so this is what an actual, right? Again, if you want to write this thing, okay, again, if you want to write this thing, the four equations, right? Okay, then we can write it as potential energy, that is equal to half m omega square a square, right, sine square of omega t. Similarly, kinetic energy, that is equal to half m omega square a square, that is cos square omega t. Another equation of the potential energy, that is equal to half kx square, right, and kinetic energy, right, that is equal to half, right, k of omega into x square minus x square, right? Okay, just hold on, I have written the wrong thing. Okay, half mv square, right, so that is equal to half m, it's a square omega square, or that is half m, and that is omega square a square minus x square. Yes, that's a perfect thing. So that will be half k a square minus x square. Yes, that's the perfect thing. Okay, so these are the first of all, we understood the actual variations of the kinetic energy and the potential energy. Right, now you can see there is in equation of the kinetic energy and the potential energy, you can understand, see, equation of the kinetic energy states that it is half m omega square a square cos, right, of omega t. What is an equation of potential energy? That is equal to half m omega square a square, and that is equal to sine square omega t. See, kinetic energy and the potential energy is also varying with respect to time, because in this also we are having the cos and the sine function, right? In this also we are having the cos and the sine function. So what will be the graph of it, right? Let's understand this graph, right? This is the mean position, right? This is the mean position, x is equal to 0, right? This is a max displacement, x is equal to positive a, right? And this is in another side, either side x is equal to negative a, right? So if I want to plot this graph, right? If I want to plot this graph, Arey yaar, I'm sorry for that, right? X is equal to 0, right? If I want to plot this, right? So at x is equal to 0, right? The velocity is maximum, the kinetic energy is maximum. Graph will be like this way of the kinetic energy, right? At x is equal to 0, velocity is 0, right? So it means kinetic energy is 0. So here the kinetic energy will be 0, right? And at this point also the kinetic energy will be 0. So the graph will be like this way, right? Okay. This is the variation of kinetic energy, right? Now at this point the potential energy is 0, right? And at this point potential energy is maximum, right? So right, so this is for the potential energy, right? Okay, now whatever the variations that are been measured, it is in between the kinetic energy and the potential energy, right? So it means the upper one graph, right, that is a straight line. Okay, the graph of the straight line, that is the graph of total energy, right? So here I want to write it down. The total energy is constant, right? The total energy is constant. In another sense, total energy, that is equal to kinetic energy plus potential energy, right? At some point kinetic energy will be maximum, at that point potential energy will be minimum. At some point potential energy is maximum, at that point the kinetic energy will be minimum. So whatever the variations will go on, it will be in between the kinetic energy. At all points the total energy of the particle is going to be constant. At all points on the path, the total energy of the particle is going to be constant, right? So this is what the graph is all about. Now let's move on, right, to the sums, right? Whatever we have seen till now, to the sums of it. Okay, now sorry. The total energy of the particle, right, executing the SHM is proportional to what? Total energy, that is equal to kinetic energy, right, plus potential energy, right? Equation of the potential energy was half k x square, right? Equation of kinetic energy was half k, right, a square minus x square. Replacing this, half k a square minus half k x square plus half k x square. This thing is gonna cancel. So the equation of total energy, we are getting half k a square, in another sense half m omega square a square, right? Okay, m is constant, omega is constant, right? So the total energy is directly proportional to the square of amplitude. Total energy is directly proportional to the square of amplitude. A is the perfect answer for this specific question. A is the perfect answer for this specific question. Very simple. Okay, now starting from a origin, a body oscillates simple harmonically. See, now we are not going to see some basic sums related to it. No. Now we are going to see the sums that are already like they have been asked. See, weightage of this chapters is quite less. That's why the PYQs are less. But it's okay, right? We are going to deal with the energy and on all of those equations, right? Okay, so it will be quite easy, right, to understand the concept also and to grab the right the clicks of the sum. Starting from the origin, a body oscillates simple harmonically. They have said particle is performing SHM with the time period of 2 seconds. Now see, time period it is given as 2 seconds. Yes, it's good. So first of all, let's calculate the omega. Omega is equal to 2 pi by t. So it is equivalent to pi radian per second square. Okay, whether it is going to help or not, but we calculated it. What will be its kinetic energy? After what time the kinetic energy will be 75% of its total energy? So they have asked at what time the kinetic energy is 75% of total energy. So it means that, can I say kinetic energy that is equal to 75%, it means 3/4 of the total energy. What is the equation of the right kinetic energy? That is half m omega square a square cos square omega t. What is the equation of total energy? Half m omega square a square. Half m omega square a square. Half m omega square a square. So we are getting cos square of omega t, that is equivalent to 3/4, right? So cos of omega t that will be is equal to √3/2, right? So omega t we are going to get, right, pi by 3. Okay, I'm sorry, not pi by 3, it's √3/2 now, so it's pi by 6. Okay, so we are going to get it as pi by 6. Now omega t value is pi by 6, right? We need to calculate at what time, right? So what is the value of omega? It's pi into time. Pi is gonna cancel time at 1/6 seconds, right? At 1/6 seconds the kinetic energy will be 3/4 of the total energy, right? The kinetic energy will be 3/4 of the total energy. At what time, right? So 1/6, at 1/6 seconds, right, the kinetic energy will be, right, 75% of total energy. A body executes simple harmonic motion. Everything, see, whatever it is coming into the questions that I have delivered in front of you, everything. A body executes simple harmonic motion. The potential energy, the kinetic energy, and the total energy are measured as a function of displacement. It's okay if they are measured in terms of the displacement, right? At mean position, x is equal to 0, it is a mean position, right? At mean position, the kinetic energy is maximum, right? Potential energy is minimum at the mean position, right? And total energy is constant at all points. Okay, sorry for that. What do you conclude from the graph, right? The frequency of the kinetic energy, potential energy, and the SHM. What do you conclude from the graph, right? What do you conclude from the graph? Just keep one thing into the mind: the frequency of the kinetic energy and the potential energy, right? Okay, one statement that I want to write in: the frequency on this, right? Many times the questions are asked. The frequency of the kinetic energy is always double the frequency of SHM. Right? Frequency, it means variations. In one oscillation, right, the variations of kinetic energies are twice at what the variations happens in SHM. Right? A is the perfect answer for this specific question. Right? Let's move on to the next question. A particle is executing the simple harmonic motion. See what kind of the questions, right? How we are using the equations of velocities in energies, right? Lots of students might be having the questions in their mind, right? Lots of the students are having the questions in their mind. Sir, why you are only giving us the questions of the energies? Why only the questions of the energies? Right, the total and mechanical and everything it is there. So the reason behind it is, right, you are having the you have done lots of practice questions, right, related to the fundamentals of the SHM, but this energy it is going to, right, this will help us, right, in covering up the basic concepts also, right, and the higher level also. Okay, so suppose if particle is executing the SHM, right, with the amplitude A, when the ratio of its kinetic energy and the potential energy is 1/4, displacement of its mean position is, see now, displacement from its mean position, this part is of the fundamentals of SHM. Ratios of kinetic energy and potential energy is 1/4, right? This will force us to use the right concepts of energies. Ratio of kinetic by potential is given as 1/4. Right, we are aware of this is the equation of kinetic energy, right? This is an equation of the potential energy, but from how we are going to replace that equation, how we are going to replace that V. So here comes the concepts of fundamentals of SHM. So that's why question based on energies are kept, right? So that will help us, because this is a crash course, so that will help us also, right, to understanding or to cover up the all of these aspects of fundamentals of SHM. Now it is given as 1/4. Can I say kinetic energy is half k a square minus x square, that is equal to 1/4, and whole divided by that is half k x square. Half k is gonna cancel, right? So that is a square minus x square into 4, and that is equivalent to x of square. So can I say a square, that is equal to hold on, just hold on. Okay, so here 4a square minus 4x square is equal to x square. So 4a square, that is equal to, right, 5x square. So the position, right, is 2 under root of a, sorry, 2a by under root of 5. I'm sorry, not under root of a, 2, right, a by under root of 5. Plus or minus. At this position, the ratios of the kinetic energy and the potential energies are getting 1/4. Right. So what does it states? This is the mean position, right? X is equal to 0. At x is equal to, right, plus 2a by under root of 5, and x is equal to, right, minus 2a by under root of 5. At both this position, the ratio of the kinetic energy, right, with respect to the mean position, the ratio of kinetic and potential energies are getting 1/4. Right? So A is the perfect answer for this specific question. Let's move on to the next part. A mass 4 kg is suspended from a spring of force constant 800 meter. Executes a simple if the total energy of the oscillator is 4 joules. See, mass 4 kg, spring constant 800 Newton meter, total energy 4 joule. The maximum acceleration of the mass is what? Now here comes the fundamentals of SHM, but still in that the energy is involved, right? Still in that the energy is involved. Now see, total energy is 4 joule. So what is the equation of total energy? That is half m omega square a square, right? That will be equivalent to what? 4 joule, right? What is the equation of the total energy of the oscillator? That is equivalent to 4 joule. So what is the equation of the total energy? That is half m omega square. Can I say it is, can I replace this both as the value of k? Half k A square, that is equivalent to 4 joule. So K A square, that is equal to 8 joule, right? So here we are getting the amplitude A square as 8 by value of K. What is A square? That is equal to 8 by 800. A square, that is equal to 1 by 100. Amplitude, that is equal to, right, 1 by 10 meter. Amplitude we are getting as 1 by 10 meter, right? Or in another sense, amplitude, that is equal to 0.1 meter. Now what is asked in question? Maximum acceleration. Okay, the equations will immediately scrolled up in your mind, right? A is equal to minus omega square x. Magnitude A is equal to omega square x, right? Can I replace this equation, right? Maximum acceleration always occurs when value of the x is getting A, right? Okay, so here we are getting value of the maximum acceleration as. Can I replace the omega square? Omega square, that is equal to K by M. So it's K by M into A. It is 800, mass is what, 4, and this is 0.1. So it is 80 by 4. The maximum acceleration is 20 meter per second square, right? A is the perfect answer for this. This includes the fundamentals of SHM and total energy. For a particle executing the SHM, the displacement x is given by this equation. Identify the graph which represents the variations of potential energy as a function. So that you are all aware of, and this thing you can do. So this question is homework from my side, right? You can answer this question beneath the video. All the concepts of uniform circular motion, all the concepts of uniform circular motion are applied to SHM. Oh. Sir, that's wrong. That's wrong, sir. So how is it possible? How we can compare the uniform circular motion, right, to the SHM, right? And how you are going to prove that? Yes, we are going to prove that stuff, right? And you are really going to enjoy, right? Phasor method is like that. Those who are going to those who explains this method, right, at the very first attempt, it is impossible to understand the 100% content of it. At the very first attempt, it is impossible to understand the 100% of it, but yes, we are going to understand, because that sort of example I'm going to keep in front. There is one disk, right? This disk, there is a disk. A small ball or a bit is attached to the disk, right? Now this disk is moving with the constant angular velocity omega, right? It is moving with the constant angular velocity omega. Constant angular velocity omega. It means I can say that this ball is performing the uniform circular motion. Is it clear? This ball is performing the uniform circular motion. Is it clear? Yes, is it clear? It is clear. Disk, a ball attached to it, it is moving on the circular path, right? Ball attached to it, it is moving on the circular path, right? Angular velocity of the disk is constant, so same for the angular velocity of the ball is constant. So this is a uniform circular motion. Sir, where is the SHM? Yes, it is going to come. Right? It is going to come, don't get worried. Okay, let's play some light here. Light is having this kind of reflection, not reflection. The rays are coming out like this way. right? The rays are coming out like this way. At the bottom, we are having a floor. Obviously, the light is going to, right, strike on the floor. Now, what will happen? Right? What will happen here? The projection of this ball, in another sense, shadow of ball, right? You can see the shadow of the ball on the respective floor. If the ball is at the position A, its shadow is at this position A. If the ball is at this position, the shadow is at this position B. If the ball is at this position C, right, the shadow is at this position. Again, if the ball is at this position, the shadow is at this position. Again, if the ball is moving at this position, the shadow is at this position. You can understand the ball on the disc is performing the uniform circular motion, but its shadow is performing the SHM. Disc, uniform circular motion, shadow, SHM. That's an example of it. The best visualization that we can compare, right? Yes, all the concepts of the uniform circular motion are applied, right, to the SHM. Again, I'm writing that statement. All concepts of uniform circular motion ball is attached to the rim, right? It is moving on, right, with a constant angular velocity, but its shadow, see, it's a uniform circular, or that's SHM, right? Okay, now see the equation, the displacement equation of the SHM is x is equal to a, right, cos of omega t, right? Velocity equation is a omega negative, right, sine of omega t, right? Acceleration is equal to negative a omega square, right? Okay, cos of omega t again. As I said, the value of the cos differs between -1 to 1. Value of the sine differs from -1 to 1, right? So for SHM, see, SHM is a kind of a to and fro motion, right? I told into the previous part of this session, right? The sine, the presence of sine and cos and its value that is changing between -1 to 0, 1 is not only the reason behind this equation that they are represented for SHM. This is not only the reason, right? If I'm talking about the position, right, the maximum displacement is A, the value of A, right? Okay, the value of the X, that is position at any time t, is varying between -A to A, right, in between, right, crossing from 0. Okay, so similarly, not only see cos, sine, you can see in this all of those equations we are having the trigonometric functions sine and cos, right? So these are not only the reason behind it. These are not only the reason behind it, right? Not only the reason behind it. Okay, these are not only the reason behind it. The phasor is most priorly included in that. Right, we wrote down that equation. Now see, now this, see, suppose, okay, you can understand, see, suppose if the light is kept on this part, okay, then particle is performing the SHM on this way. So for this displacement equation, we can write it down, x is equal to a cos of omega t, right? Now suppose if I'm changing the position of the light, this is a great confusion that students are facing. Suppose if I'm changing the position of the light, if light are kept on this way, right, now the shadow will perform the SHM into the vertical direction, right? Shadow will perform the SHM as it is performing in the horizontal part also, right? But the light projections will fall like this way. Light projections will fall like this way, right? Okay, and for this we are having the equation of SHM as y is equal to a sine of omega t. This is the difference, guys, right? This is the difference, guys, right? This is the difference. Okay, y is equal to a sine of omega t. Okay, so if the particle is moving onto the circular path performing the uniform circular motion, so it means, right, the light projections, right, the shadow of the particle is performing SHM. It means all of those concepts, right, of the SHM we can apply to the uniform circular motion. And now let's see what actual the phasor is. Phasor. If I want to define the phasor, then it is a rotating vector. As I used to say in all of my lectures, in the amples of resources, right? Okay, hundreds of definitions are given, but simply if I want to define the phasor, then it is the rotating vector, right? You can see into the visualizations also, right? Okay, suppose, see, this is a path. Sir, you said that uniform circle, all the concepts of the uniform circular motion, right? It is an analogy that all the concepts of the uniform circular motion can be applied to the SHM. Sir, it's okay. We understood. But right now lots of shortcuts are going to come. Now this half an hour, the next half an hour will be completely full of shortcuts. Full. If for the equation y is equal to a sine of omega t, right, just mind down, this will be plus a, this will be minus a. For a motion, right, for a vertical SHM, this is the criteria. If you want to move on for the horizontal SHM, see, vertical SHM, it means that, see, horizontal SHM is like this way, right? Horizontal SHM is like this way, right? Horizontal SHM is like this way. So, okay, so one is a horizontal motion, second one that is, sorry, there was a technical glitch. This is for horizontal SHM, this is for vertical. For vertical, we are having this is plus a, this is minus a, this is a mean position, right? For horizontal and vertical, mean position is same, right? For horizontal, this will be plus a, right? This will be minus a. What is the phasor? Phasor will be the rotating vector, right? Okay, that rotates with the constant angular velocity omega. Phasor is rotating vector that rotates constant angular velocity omega, that rotates with the constant angular velocity omega, right? That rotates with the constant angular velocity omega. Okay, so in this case, it rotates with the constant angular velocity. Okay, now let's move on to the understand this thing into the detail. Okay, see, I am talking about, right, the SHM into the vertical direction, right? We are going to take that example to understand this topic into this detail, right? Because using this topic, I think, right, the lengthisms are going to solve into the very few steps. Okay, see now, for vertical, this will be plus a, this will be minus a. Suppose if I want to represent the phasor first, suppose, right, if I want to draw this phasor diagram for the equation, y is equal to a sine of 2 pi t, a particle that is performing the SHM, and that equation is represented by this. A is an amplitude. What is the value of the omega? Omega, that is equal to 2 pi, right, radian per second. Omega, that is equal to 2 pi radian per second. Okay, omega, that is equal to 2 pi radian per second. So this is plus A now. Initial phase is 0. It means what? Phasor starts from t is equal to 0. Initial point for phasor. Right. Now it is rotating with a constant angular velocity 2 pi radian per second. Right. So in 1 second, it is completing the entire circle. In another 2 seconds, it is continuously like completing the entire circle. So it means after time t1, phasor is in this position. After time t2, the phasor in this position. After time t by 4 or some t time, right, phasor is at this position. Then it will move on to this position. It will move on to this position. It will move on to this and final to this. Like this way, it is rotating continuously. Now students are getting confused. Sir, basically there are two ways of phasor rotation. One into the anti-clockwise direction, into the clockwise direction. While moving on into the anti-clockwise direction, right, the answers will differ, right, as compared to moving on into the clockwise direction. So what the correct method is. So for that, I want to write it down. Phasor always moves in the anti-clockwise direction. Phasor always moves into the anti-clockwise direction. Always. Right? Why? Because angle. There is one property of there is one noteworthy point of an angle. When we saw this thing into the units and measurement, there is one noteworthy property. What is that? Angle is always calculated with respect to the positive x-axis and in anti-clockwise direction, double quotes. Again, I am highlighting this statement. Angle is always calculated with respect to the positive x direction into the anti-clockwise direction. Same way, right? The same thing is for phasor. It is always calculated with respect to the positive x-axis, right, and into the anti-clockwise direction. It always rotates. As I said, phasor rotates with the angular velocity omega, yes, but it always rotates into the anti-clockwise direction. Phasor, right? Okay, so suppose, let us take an example. Okay, now suppose in question it is written a particle is performing the SHM, y is equal to, right, 10 sine of 2 pi of t plus pi by 3, right? If this is an equation of a particle that is performing the SHM, draw the phasor diagram. This kind of the question, see, basically 3 to 4 kind of questions are there, right? And in the see, phasor method is also useful into the cases, right, where superposition of the SHM is also, right, studied. Okay, so now suppose if I want to draw the phasor for this, right, so this is a phasor diagram. Okay, see, 10 is an amplitude, so this will be the value plus 10, right, this will be the value minus 10. This is the y, it means the SHM is in the vertical direction. What is its path? This will be the path of the SHM, right? Slowly we are going to calculate the velocity into the very rapid manner. Slowly we are going to calculate, right, okay, the acceleration into the very rapidly. I'm going to show you all the shortcut for this, but first of all, let's see some basic sums related to it, then we are going to see some shortcuts. Initial phase angle is pi by 3, right? So this is pi by 3. This will be the initial point of the phasor from which it is going to start to rotate with the angular velocity omega. This is in phasor diagram, right? Now let's move on to the sums related to it. Okay, then you are going to understand this stuff. Now see, first question. The figure shows the circular motion of the particle. The figure shows the circular motion of the particle which is at the topmost point only on the y-axis and t is equal to 0. The radius of the circle is also given. The simple harmonic motion of the x projection, see, it's mentioned. we need to identify the correct equation. It is given x projection, it means that, right, it is given the x projection, it means that this is the motion, this is the path of the SHM of the particle. This is the path of the particle, right, performing SHM. Now, at t is equal to 0, initial position is this. It means particle is starting from mean position. Right? Particle starts from mean position. Particle starts, right, from x is equal to 0. It means initial phase is 0. Time period is given as 30 seconds. So time is equal to 30 seconds, 2 pi by capital T. That is equal to 30 seconds. T is equal to 2 pi by 30. I'm sorry, yaar. 2 pi by omega. Right? So this will be the angular velocity of the rotating vector phasor. Now, if I want to represent this equation, then x is equal to a, right? X is equal to a. You can see this, right? Okay. Now, what is the max displacement? It is given as b, right? B is the max displacement. You can see the radius of the circle. The radius of the circle is its amplitude and it is the max displacement, right? Initial phase is 0. So can I say the equation of the particle, right? X is equal to a sine of omega t plus phi. Initial phase angle is 0. Amplitude is b, right? Initial phase angle is c. 2 pi by 30 into t, right? This is the correct equation of the SHM of the particle using phasor, right? A is the perfect answer. Now let's see the magic. Particle executes SHM if the time taken by particle to minus a to a by 2 is 4 seconds. Its time period is what? Now see. This is positive A. This is negative A. Particle is moving on from minus a to plus a by 2. See, as I said, phasor always rotate into the anti-clockwise direction. Minus a by 2 comes here, right? Okay, minus a to a by 2. I'm sorry, it's moving on from minus a to a by 2, right? So see, minus a is here, right? A by 2 is somewhere here, right? So this is an initial position on the phasor, right? This is a final position on the phasor, right? I'm going to show you all the difference, what is an actual method and how a phasor is resolving and saving a time, right? How phasor is resolving and saving your time, right? So here I think okay, so in between initial and final points, right? Okay, the phasor always rotates into the anti-clockwise direction. So suppose it is moving into the anti-clockwise direction, right, with the angular velocity omega, right? The difference, the time difference between the initial and final points, it is given as 4 seconds. Now what is an actual method? Y of a sine of omega t plus phi, right? First we are going to replace for minus a, and then we are going to calculate for t1. Second, we are going to replace for a by 2, then we are going to calculate for t2. In both of the cases, we are going to replace, right, the value by the 4 seconds, and long calculations we are going to do to find the time period. But this thing can be solved easily by means of phasor, right? How? What is the phase difference? Just always calculate the phase difference between these 2 points. This is pi by 2, right? Okay, always move into the anti-clockwise direction, right? This will be pi by 6, right? One is pi by 2 and second is pi by 6. What is an actual phase difference? The phase difference between the initial points and final point, that will be pi by 2 plus pi by 6. So that will be equivalent to 2 pi by 3. It is moving on, see, we need to calculate the time period, and it is moving on with a constant angular velocity omega. A very simple step. Omega is equal to phase difference by delta t. Delta t is given as 4 seconds, right? Okay, so omega, that will be equivalent. What is the phase difference? 2 pi by 3 whole divided by 4 seconds. What is the value of omega? 4 omega, that is equal to 2 pi by 3, right? So it will be 4 into 2 pi by capital T. Omega I am replacing by 2 pi by capital T. That is 2 pi by 3. This 2 pi is going to cancel. T is equal to 12 seconds. This is the time period of the SHM. A very simple calculation. And the very first attempt, I can understand it will take some amount of a time to write, okay, to understand, to grab this thing. But if you have done this, right, I assure you the difficult sums can be solved within few steps using just a single formula. Okay, this is the same sum. It has been repeated. Okay, now. See now. How we can calculate, right? Okay, just by the geometry we can calculate the velocity and acceleration at the each point. See, suppose this is a 10 centimeter negative, the amplitude. This is a positive 10 centimeter as the amplitude, right? Suppose a particle that is performing the SHMX, that is equal to, right, 10 sine of 2 pi t. We need to calculate the velocity, right? We need to calculate the velocity, right, at x is equal to 6 centimeter. We need to calculate the acceleration at x is equal to 6 centimeter. Again, that long formula based calculation. No, we are going to solve it quite easily using Phasor. This is plus 6 centimeter. This is an initial position of the particle. Right? This is the final. Very simple thing. See, this is a radius. It means it is 10. This is 6. What will be this angle? Right? It will be 10 of phi. Right? That will be equivalent to 6 by 10. So that will be equivalent to 3 by 5. Phi, that will be equivalent to what? 37 degree. Right? Okay. So this will be 37 degree. This angle will be 37 degree. At this position, as I said, all of the concepts of the uniform circular motion can be applied to this. So velocity, for a uniform circular motion, velocity is always tangent to the path. There are two components. One in this direction, one in this direction. Right? You have to just calculate. Suppose this is 37, this is 37, right? This is 53. This component will be V cos of 53, V sine of 53. This will be your answer because it is lying parallel to the path. Right? See. Now, acceleration. The radius is 10. Right? Okay. This is 37. Now acceleration always acts towards the center and it is moving on the circular path. Then that we can compare it to the centripetal acceleration. This is the component A cos of 37. This is the component A sine of 37. The component that is acting parallel to the path will be our answer. So at 6 centimeter. This will be our acceleration and this will be our velocity. This is as much easy as you are thinking right now. Yes. This one is homework from my side. It is a very simple sum based on the phasor. Now, I'm going to show you all one shortcuts, right, on the base of the time period of the SHM. I'm going to show you all some shortcuts on the base of the time period of the SHM. There are some cases, right, in which the time period of SHMs are asked. Like suppose this is a spring, this is mass M. If gently push is given, a gentle push is given, then obviously it's going to start performing SHM. What will be its time period? T is equal to 2 pi, right, under root of M by K, correct? This is an actual formula. Now, suppose if two springs are connected in parallel, right? What will be the formula of time period of SHM? T is equal to 2 pi under root of M by K equivalent. T is equal to 2 pi under root of this thing, all of these things, right? Okay, some part of like this concepts we have seen into the work energy of power while dealing, right? We have seen that when what will happen when springs are connected in series, right? What will happen when springs are connected in parallel? So in parallel, K equivalent, right, that is equivalent to K1 plus K2, right? So final time period equation of the SHM is under root of M by K1 plus K2, right? Suppose this is a case of the parallel connection of the springs. Suppose the series connections of the springs it is given. This is a spring of the spring constant K1, another spring of the spring constant K2, right? And they are connected in series. This is K1 and this is K2, right? One it is connected in parallel, second it is connected in series. So in this case, K equivalent, right, we are having when they are connected in series is K1 K2 whole divided by K1 plus K2. So the time period for this, that is T is equal to 2 pi under root of M whole divided by K1 K2 whole divided by its K1 plus K2. This is the time period of the SHM. This is a very basic formulations. Now in this, right, 2 to 3 methods are there, right? Okay. Sums based on this in JEE mains and advanced they are asked, right? A lots of pulleys and spring mass systems are given, a complicated systems are given, and we need to calculate the time period of the SHM of the particle. Right, we need to calculate the time period of the SHM of the particle. And today we are going to see that stuff into the very simplified form. Shortcut I am going to show you in front of you all. The mains and advanced level sums based on this shortcuts, right, we are going to solve. Now let's see what actual the shortcut is. Right, today I'm going to give you all a solution for a most critical problem. Let's see. Right, suppose one arrangement it is given like this way, right? One arrangement it is given like this way. Okay, and we need to calculate the time period for the SHM. Pulley mass system is there with springs attached to it, right? Okay, for this a displacement method is there and blah blah, lots of things are there, but I'm going to provide you all a shortcut, direct shortcut, no need for anything, and that shortcut is applicable for everywhere. Right? The shortcut states the formula of the time period is T is equal to 2 pi under root of M by K equivalent. right? This is a formula that you need to remember for all of those cases. What will be the value of the K equivalent? That will be K of spring tension on block by tension on spring whole square. Sir, suppose if it is about more than one springs, then how you are going to solve? I'm going to show you all, right? And most critical sums we are going to take. Okay, just to remember these two things, right? And now we are going to solve the sums. Let's see. First, suppose if it is arrangement, it is given like this way. All of those critical sums I'm going to take. The arrangement is like this way. Right? This is a spring of the spring constant K. This is of the spring constant K. We need, suppose if the gentle push is given to the block, then we need to calculate a time period for the SHM of the block. What will happen? Right? What will happen here? Right? It's a very simple thing. Right? What will happen here? Again, that displacement we are going to calculate it. No. Simple one shortcut. See, first of all, what will be the tension on the block? T. What will be the tension on this spring? T. What will be the tension on this spring? 2T. Two springs are there, na? N numbers of, for this shortcut, N numbers of springs are there. Consider all into the series. Right? Now see, very simple thing. For spring 1, this is spring number 1, this is spring number 2. Right? Can I say K1? That is K for spring, right, into tension of block by tension of spring whole square, right? So can I say K1, that is equivalent to what? K of spring is K. It's K. What is the tension of block? T. Tension of spring T whole square. Can I consider this as equation number 1? Yes. For spring 2, right? Can I say K2, that is equal to K of spring into tension of block by tension of spring whole square. What is tension on block? T. Tension on spring 2T. So can I say K2, that is equal to K, right? Tension on block T, this is 2T, right? Whole square. So K2, that will be equivalent to K by 4. Can I consider this as equation number 2? Two springs are there, na? Using the shortcut, we calculated that part. Now consider both in series. Whatso arrangement it is given, consider both in series. What will be the K equivalent? That will be equivalent to K1 K2 whole divided by K1 plus K2. Right? So it will be K dot K by 4 whole divided by 5K by 4. So this K by 4 is going to cancel. K equivalent, we are going to get K by 5. What is the time period? T is equal to 2 pi under root of m by K equivalent. So T is equal to 2 pi under root of 5 m by K. This is the time period of the oscillation for the object. Shortcut. Let's take another sum to understand this stuff. Suppose if this arrangement it is given, this is K, this is K, this is K. We need, suppose if the gentle push is given, we need to calculate the time period for the SHM of this blocks. A most weird arrangement, right? I'm damn sure, suppose if this kind of the arrangement is asked into the JEE mains or right advanced level examination, you are going to, right, I'm damn sure you will fail to apply the regular method, but this shortcut is going to help, because in this kind of the examinations, right, we are not moving on to the theoretical approach, right? That's why. What is the tension on the block? Suppose here the tension is T, 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 T and T, right? Here we are having 2T, here we are having 2T, here we are having T, and here we are having T. The tension on the block 6T. How many springs are there? We are having 3 springs, right? We have to consider all in series, but calculations are individual. For spring 1, right, K1 that is equal to K of spring, that is K, tension on block by tension on spring, right? All of the springs are having the same 2T, 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 right? Okay, so it's tension on block by tension on the spring 6T, right, whole square. This is gonna cancel, right? So it is equal to K by 9. For spring 2, again the calculation is going to be K by 9. For spring 3, again the calculation is going to be K by 9. Consider all in series, right? 9 by K, 9 by K, right, and 9 by K, okay, and 9 by K, that is 1 by K equivalent, right? Okay, so what will be the K equivalent? That is K by 27, right? What is the time period? T is equal to 2 pi under root of, right, 27 m by K, right? Okay, so it's 9 3s are 27. T is equal to, okay, 6 pi under root of 9 into 3, so it's 3m by K. This is the time period of the SHM of the block. A very critical case you are going to solve using sums. So this is how the time period of the right SHM is being calculated. Right, now let's move on to the most important and the last point of this chapter. Right, okay, see, according to the JEE and NEET point of view, whatever it is coming, I'm showing you all in front. Okay, now let's move on to the most important thing, and that is, see, suppose if I'm taking an example of a pendulum, right, this is in pendulum and this is in a bob connected to it, right? Okay, now suppose if the gentle push is given to the bob, if the gentle push is given to the bob, then obviously it is going to oscillate, right? On the either side, right, this is going to be the maximum displacement, right, of the, this is going to be the maximum displacement, right? In another sense, maximum angular displacement of particle, right? Maximum angular displacement is phi. But with respect to time, suppose at t is equal to 0, the bob is released. With respect to time, slowly, the angular displacement is getting increased, right? The angular displacement is getting increased. So if I'm talking about any time t, the displacement is theta, right? The displacement is theta, and at that time the angular, or you can say, we can say it as an x, and this is amplitude A, right? So can I say x that is equal to L of theta, and amplitude that is equal to L of phi, right? For SHM, restoring force is responsible. For angular SHM, restoring torque is responsible, right? Here one restoring torque is there. Suppose this is mg, right? Here we are having the component mg sine of theta. This is going to create one restoring torque because it is included into the, say, in cases of the rotational motion, torque is only responsible for a particle to come back to its original position. In SHM, it was a case of the translatory motion, so that's why restoring force was responsible, and in the cases of the angular SHM, restoring torque is responsible, right? So yeah, if I'm talking about for bob, the equation of SHM is represented as x, or in another sense, I've taken it as an x, so I'm taking it as an x, and that is equal to a sine of omega t plus phi. So can I replace x as L theta, a as L of phi, and that is sine of omega t plus phi. So L will get cancelled out, so theta is equal to phi sine of omega t plus phi. So in the case of the angular SHM, this is angular displacement, right, at any time t. Phi angular displacement that is maximum. In case of SHM, we were having x or y, that is equal to a sine of omega t plus phi. Here a was maximum displacement, here it is phi is maximum angular displacement. Here x what position at any time t, here this is angular displacement at any time t. This is what an actual difference between SHM. Right. Now, suppose we got this equation, right? See, the angular displacement at any time, that is phi sine of omega t plus theta. Now, differentiating this equation with respect to time, what we are getting, that is d theta by dt, angular displacement with time, that shows the case of angular velocity, and that is equivalent to what? Phi, right, into omega, and that is cos of omega t plus phi. This shows the case of the maximum angular velocity, right? Or you can say the angular velocity amplitude. Again, differentiating this equation with respect to time, right? What we get, alpha, that is equal to minus omega square theta. This is the condition, right? We were having one condition. Say if the particle is satisfying this equation, a is equal to minus omega square x, we can say the particle is condition for particle to perform SHM, right? Similarly here, alpha is equal to minus omega square theta, condition for particle to perform the angular SHM. This is only the differences, right? Now with this, one another example is just suppose how to calculate the time period for this kind of things, for the rigid bodies, right? Again, for this I'm taking one example of a bob. Suppose this is a bob, right? And it is having some angular displacement with respect to time, right? Suppose this is at the max position, this is phi, right? Okay. I must say into the previous one, thetas and everything are colliding. Okay, this is not phi. We are changing the angle as alpha because it is of the SHM. We are changing it as an alpha, right? I'm sorry, we are changing it as an alpha. Okay, this is an alpha because I think more than two symbolic notations are there. That's why we are changing it as an alpha, right? Okay, here also we are changing it as, it's okay, alpha. Okay, because three angles are there. Now, one, this angle is for the bob who's performing the SHM, right? This theta is angular displacement at any time, and this phi is a maximum angular displacement. These three are the different phase angles. Sorry, different angles, right? Okay. Now, mg is acting into this direction here. Mg sine phi. This is responsible, the restoring torque, right? The restoring torque is responsible for particle to perform angular SHM. Restoring torque is right of a particle is right, okay, responsible for. So can I say that restoring torque is directly proportional to theta as force is directly proportional to displacement? Removing the proportionality sign, can I say torque is equal to k theta, right? Okay, On the opposite side, if torque is equivalent to negative k theta, what is the condition, right? Can I say this torque is directly equivalent to I alpha also, right? So it means I alpha is k theta, right? So here what happens, I'm sorry, just hold on, right? We are going to do this derivation. Okay, see, now I alpha is directly proportional to k of theta in terms of the magnitude, right? Okay, so I, can I say alpha, right, that is equivalent to k by I of theta. Can I compare this to, suppose if you are keeping a negative sign here, can I compare to minus omega square theta, that is k by I into theta, negative, right? So here what we are getting, omega that is equal to k by I, right? So here 2 pi by t, that is equal to k by I, right? Here t is equal to 2 pi under root of, right, it's omega square, na? So it will be under root of I by k, where I is the moment of inertia and torsional constant, k is, or you can say proportionality constant, right? K is proportionality constant. This is how, right, the time period of the, right, SHM has been calculated. Okay, the time period of SHM is calculated. So this is how, what an actual difference between, right, the angular SHM and SHM, right? Okay, there are some important formulas that I showed in front of you all. I want to show you all one simple example in front. This is the mean position of the particle. X is equal to 0, t is equal to 0. It is a mean position, right? Now from the mean position a gentle push is given and it is released, right? Gentle push it is given and it is released. Now what happens here, right? A gentle push it is given and it is released. Now what happens here? Now see here, suppose this is a spring constant of now. Is there any kind of the dissipative forces it is present in the surrounding? Generally all of those cases we are considering, right, into the vacuum, right? I'm not saying about the gravity free space, right? But in environment, no atmospheric pressure is acting and no air resistance is there, this kind of things are there. But here, if I'm talking about the practical terms, first, are surfaces perfectly smooth? In the beginning part of the session, we consider the surface as smooth. Practically, is it possible that for any surface mu is 0? No air resistance, no damping. Is it possible? I must say no. Right? To understand the concept into the convenient manner, we always used to consider as no energy loss. We also considered one most important point, that total energy of the SHM at all points, right, is constant. Is it for sure? Because while considering the total energy of the constant, right, work done by non-conservative, work done by external, that is equal to delta K plus delta U. Did we consider any work done by non-conservative forces? Generally, the dissipative forces are considered into the non-conservative. Did we consider that? No, we consider it as a 0. Did we consider any external agent? No. That's why the total energy of the SHM is conserved. It is constant at each and every point. But here, damping means there is the presence of any external force. If I am talking about SHM, in absence of any external force, in absence of any external, right, force, what is the responsible thing for the SHM? Right, F is equal to the restoring force is a responsible thing, right? So here, if I am replacing M into A, that is equal to minus Kx. M into dV by dt, right, that is equal to minus Kx. Okay, now here if I am replacing M into d square x by dt square, right, that is equal to minus kx. It's m d square x by dt square, right, plus kx, that is equal to 0. This is the differential equation of the SHM that states there is no presence of any kind of the damping forces. If there is no presence of damping force, then and then F is equivalent to minus kx. Here, actually it should be any dissipative, right, or any damping force is there. If this is 0, then and then F is equivalent to minus kx, and we are considering the pure SHM, the ideal situation. In practical life, it is not possible. Now, what is the role of this damping force? We consider the total energy as constant at all points. Damping force, right? What does this damping force does? Let's analyze this example. The day-to-day life example of this swing, right? Okay. So in SHM, F is equal to minus kx, differential equation m d square x by dt square plus kx, that is equal to 0. No damping force is present, right? The next point, total energy is constant at all points, right? Total energy is constant at all points, but damped oscillations, total energy decreases, right, with respect to time. Total energy decreases with respect to time. You can see one example, swing. Our day-to-day life example of the park, we used to move on with siblings, or generally if I'm talking about myself, then I used to move on to the park with my daughter, right? Okay, with my daughter. So whenever she used to swing, right? Okay, every time, if I'm if I'm giving her a force once, then for a while it starts swinging, and slowly it stops. Is there any kind of the presence of the damping force? Yes. Is there any kind of the presence of the damping force? Yes. Is there any kind of the resistive force acting? Yes. If resistive force is not acting, then on applying the force once, that swinging should continue till infinite time. But is it happening? No, it's not happening. Is it happening? No, it's not happening. Is it the same thing? No. So what happens here? Right? One resistive force is acting that slowly acts against the motion of the particle, and that decreases the total energy with respect to time. And that force that is acting, that dissipative resistive force acting, it is known as a damping force. Damping force is always directly proportional to the negative of the velocity. Why? It always opposes the motion. Always opposes the motion and try to stop the SHM. And for that reason, the energy, the total energy is decreasing with respect to time. The graph of the total energy like this way, but it's okay, right? Actually it's like this way. Right? So it always, the damping force always opposes the motion. The formula of the damping force, it is 9. Right? Now suppose if I'm talking about the same example, right? This is a spring attached and this is a mass m, right? Here let us take an example, kx is acting into this direction, and obviously in this direction there is a damping force that always opposes the motion of the particle. right? There exists a damping force, right, that always, right, opposes the motion of the particle, right? So here the differential equation we can represent it as minus kx minus bv. This is the part of the damping force, right? Okay, so here the differential equation is d square x by dt square plus kx plus bv, that is equal to 0, right? And among them b, that is known as damping constant. Now in this presence, right, okay, the actual, see, let's compare the equation of the SHM and the damped oscillations. In the equation of the SHM, I must say, in the equation of the SHM, right, and the damper, in the equation of the SHM, x was a cos of omega t. In the damped oscillation, x, it is given as a 0 e raised to minus bt by 2m, right, and cos of omega t. This is how the displacement is varying with respect to time, right? Here the total energy is constant, right? Here the total energy decreases with respect to time. Here the maximum displacement is this. Here the maximum displacement is calculated by this formula. This is an actual difference between the damped oscillations and the actual SHM that we have studied till now. What about the forced oscillation? A very simple concept. Suppose, let us take a very simple example. If the gentle push it is given, right? A gentle push it is given, right? A gentle push it is given. Slowly, the object is starting performing the SHM, and as because of the presence of the damping forces, right? As because of the presence of the damping forces, slowly, the energy is getting decreased, and after infinite amount of the time, right? After infinite amount of the time, right? Okay, after infinite amount of the time, slowly it stops. Now what happens here? If we want to continue its motion, then there is a need of an external forces, and here comes the concept of the forced oscillation. If we want an object to continue its SHM, right, we need external forces, right? And here comes the concept of the forced oscillation, right? If the total energy is slowly decreasing with respect to time, slowly it is decreasing with respect to time, and finally it is getting to 0 and object stops. So in that case, I want to tell you all, if energy is decreasing and the rate of decreasing is not uniform, in damped oscillation, right, rate of decreasing in amplitude, rate of the decrease in amplitude to stop, it is A is equal to A0 e raised to minus bt, where B is a damping constant. This is the, right, it is not uniform. So suppose if this is a not uniform thing, then we need a external force that should also be not constant in nature, right? So in this case, we need external force that should not be constant in nature. So for that reason, right, see, now you can see in the swinging, the same example we are taking. Suppose if I am applying, my daughter is sitting on that thing, right, and if I'm applying a force, right, and it starts swinging, after some amount of the time, the total energy is slowly getting decreased, right? Now there comes a situation, if I want to maintain, right, my daughter, right, she screams, "Papa!" I got a signal, I need to apply the force. Now what I used to do, first I applied a high amount of the force, then low amount, then now here comes the situation when, right, the particle is, right, when the particle starts, right, comes in its original state, then what I used to do, right, there is a difference, right? I'm comparing this thing to the day-to-day life examples, right? So it is easy to understand. So here, right, whatever the amount of the net force is there, it is minus kx, damping is present minus bv, plus one external force that should be, right, vary with respect to time. That kind of the force we need to apply. Here comes the concept of the forced oscillations. We are trying to apply that kind of the force that, right, maintains the state of the SHM. Slowly it will increase the total energy and can reach up to the, right. So this will increase the total energy, right, with respect to time to peak value. Now here comes the situation resonance. While crossing on from 0, see, it was swinging, particle was performing the SHM. As presence of the damping forces, slowly it reaches to 0. Now one external force of this value is applied. Now slowly, right, it is trying to gain, okay, some amplitude. Now it is reaching to the high value, okay, finally it is reaching to the peak value. So this is journey from 0 to peak. When external force is applied, it is journey from, right, a particle is not, now on applying the external force, the particle is not, it is not trying to attain to maintain the state of the SHM. No, now the amplitude is going to get continuously increased. So in that case, one situation arises. First of all, I am going to write down the differential equation, md square x by dt square plus kx plus bv plus f0 sine of omega t plus phi. Now on applying an external force, one situation arises where the frequency, right, of oscillator matches the natural frequency. Suppose initially the frequency of the SHM was 2 pi. Now here comes the damping force. Slowly it decreases to 0. Now again external force is applied. Now value is increasing from 0 to pi by 2, pi by 3, pi by 4, like slow. It is increasing, it is reaching to pi. Finally, it is reaching to 2 pi. So whenever the external force is applied, there arises a situation, right, where the particle is about to oscillate with its natural frequency with which it was oscillating without damping. That situation, it is known as resonance, and at that point of time the particle, right, is oscillating with the frequency, the amount of frequency is known as what? The resonant frequency, right? This much part is only there, and in this also in 2002 and 2004 and 5 sums are asked. Since 5 to 7 years questions based on this are not asked. So it's a very simple thing we are going to see, right? When an oscillator completes, see, the question is asked in 2002. It's a very simple concept, but at some of the channels, right, this thing are kept into the quite complex way, and with this lots of sums of NLMs and everything are kept extremely, I must say, right, whatever the things I'm presenting in front of you all, this much is only needed, not more than that, right? Apart from this, right, lots of things are there. Okay, when an oscillator completes the 100 oscillation, its amplitude reduced to 1/3 of the initial value, right? On completing the 100 oscillations, right, amplitude reduces to 1/3. On completing the 200 oscillations, what will be its new amplitude? Now see here, amplitude is getting reduced. It means by seeing the question, right, we are easily able to understand. This is a case of the damped oscillations, and we need to apply this equation. A is equal to A0 e raised to minus bt. So what happens here? A0 by 3 is equal to A0 e raised to minus bt, right? On completing the 100 oscillations, right, this thing is happening, right? So e raised to minus bt, that is equal to 1 by 3, right? So bt value, that is equal to ln of 3. And I consider this as equation number 1. Yes. What will happen on the completion of the 200 oscillations? Right? What happens on the completion of the 200 oscillations? Right? Okay. When an oscillator completes the 100 oscillation, okay, the time period of the one oscillation is t. The time period of the one oscillation, right, it is t. So let's compare this to equation, right? Okay, so here first of all, can I say A0 by 3, that is equal to A0 e raised to minus b into 100 by v. Can I consider this as equation number 1, right? Now, okay, this much is enough, but I think this much is enough, right? This much is enough, right? Now, okay, now let's solve this. Okay, now for the 200 oscillation, can I say value of a is A0 e raised to minus b into 200 by v, right? So taking ratio of 2 by 1, right? So we are getting a whole divided by A0 by 3, and that is e raised to minus 100b whole divided by e raised to minus 200b by v. So solving this, we are getting a is equal to A0 by 9, right? D is the perfect answer for this specific question. Okay, same equation we are going to use, but it's okay. So simple this equation. On this equation, the questions are asked. See, again, it is asked in 2003. In the case of the forced vibration, the resonance peaks are very sharp when, see, when there is one resonance curve, right? When the resonance curve is quite sharp, it means that on application of an external force, right, the frequency of the oscillator, we have discussed the resonance situation. The frequency of the oscillator is trying to match the natural frequency. It is matching the natural frequency of an particle that is performing SHM in absence of damping. But damping is in that situation, I must say, right, we can't completely avoid damping part. So for that, it is negligible, right? So in the case of the resonance, when the external force is applied to a particle, slowly the frequency of an oscillator is increasing, and at one moment it is reaching to the, right, at one moment it is matching up to the natural frequency. At that point, a resonance occurs, and in resonance condition, damping force is quite small. So students, it was all about the SHM. So I will be waiting for all of your feedbacks beneath the video, right guys? This is Indrajit Singh. Again, we are going to come back with the last lecture of this victory batch, and that is waves, right guys? So this is Indrajit Singh signing off from the desk. Bye bye. Sat Sri Akal and Namaste from my side, Bacha ji. Bye everyone. Stay at home, stay safe, stay healthy amidst this pandemic. Bye Bacha ji.